Welcome back. In this video, we're going to be introducing the topic of kinetics. So kinetics is different from what we have been discussing of kinematics in that now we are going to take into account things like forces, work, power, energy, momentum, impulse, any of those types of phrases. When we see them in the type of work that we're going to be doing, it's a clue and a hint to us that the methods that we need to understand to solve or to compute whatever dynamic quantity of interest, that we're going to need to be using kinetics. So in kinematics, we simply move from position to velocity to acceleration using calculus. And in kinetics, we're going to be using the principle that Newton has developed for us, based mostly on his second and third laws that allow us to relate force, mass, and acceleration, and thereby also energy, impulse, and momentum. So first of all, I want to give you the keyword hints. So when we are looking at problems or we want to understand how much force something is going to take, so if we see the word force or power, energy, momentum, as well as impact. These are all keywords that tell you that the type of property or the type of behavior that you're thinking of in a physics perspective is kinetic energy, or the kinetics of what's happening in our system. So in different videos, we'll talk about different tools and methods that correlate to using power, impulse, energy, impact, things like that. But we're going to focus on force to begin with. So the method that we're going to use, built on Newton's second and third law, is called the force, mass, acceleration method. So force, mass, acceleration method. And I'll often just abbreviate this as FMA, the force, mass, acceleration method. Force, mass, acceleration method applied to a particle, applied to a rigid body, applied to a system of particles. We're going to look at this different ways we can look at the force, mass, acceleration method. So as I'm sure most of you are aware, when you look at, when you think of a force, you know that the force equals mass times acceleration. This is a thing that has been hammered into kids' heads since middle school. So we're going to deep dive into that and actually understand why that is true. And to do that, we need to work with Newton's three laws of motion. The first law applies to inertia. Basically, an object that is not in motion has to have some amount of force acted on it in order for it to begin having motion. Or if it's already in motion, there has to be some forces acting on it to stop that motion. So an object in motion stays in motion. That's typically how the first law is phrased. The second law is where we get the name for our force, mass, acceleration method. And that is, if we take a mass and it is moving, the acceleration of that mass has to be proportional with respect to the mass of the resultant forces that are acting on it. And not only that, we're going to be using a vector approach so that the direction of the forces are important for us. So if we know the resultant direction and the resultant magnitude of the force, then we can compute force equals mass times acceleration and find both the magnitude and the direction of acceleration. Finally, the third law, which will have implications in terms of looking at systems of particles as well as when we think about inertia, is that all motion, all action has an equal and opposite reaction, as that's often phrased, but more precisely, an action has a collinear reaction that is of equal magnitude and in the opposite direction. So that concept, of course, is when you are standing on the ground is pushing back up with you. If you drew a free body diagram, you would have your weight going down and a normal reaction coming up. If one of those forces wasn't there, then by force equals mass times acceleration, you should be accelerating through the ground, or the ground should be accelerating you up. So of course those forces have to be here, and they have to be collinear, in a line, and they have to be of equal magnitude and in opposite directions. Finally, sort of point to take home is we're going to use the phrase force quite a bit. And so the units of force for dynamics purposes is either newtons or pounds, depending which unit system you're in. A newton is the force it takes to move 1 kilogram at an acceleration of 1 meter per second squared. And a pound force is how much it takes to move 1 slug a foot per second squared at that acceleration. So slug is a mass in the imperial US system, and a pound is a force, whereas a newton is moving that. So if you're not familiar or not intimately aware of newtons and kilograms, because you're raised in the US system, for example, a newton is about the weight of an apple on the surface of the earth. So that kind of gives you a good mental image of how much is a newton. An apple weighs about a newton of force pulling down on it, which maybe is where the story of the apple tree comes from. I don't know. So let's get into this. So the force mass acceleration method is summed up by saying that the resultant force is equal to the mass times the acceleration. So the resultant force means we have the sum of all the forces acting on a particle, and it's a vector, of course, has to be equal to the mass of that particle and the acceleration of that particle. So if we had some particle and it's being acted on by a bunch of different forces, F1, F2, and F3, what we are saying is that force, the result of all of those forces, I add them together from a vector perspective, has to be equal to the same thing as this particle having some mass times acceleration vector. So these are two important diagrams. The one you may be familiar with, we call it a free body diagram. So a free body diagram shows forces acting on an object, in this case a particle, because that's what we're talking about in particle kinetics. So this is a free body diagram. And this side is called an effective force diagram. So this resultant equivalent mass times acceleration is what's called an effective force. Whereas everything that's over on this side, the sum of F, that is your resultant force. So the point of Newton's second law is that these resultant forces must be equivalent to an effective force, the mass times the acceleration. And then they'll both be vectors, of course. So that is basically the implication of that's the whole of the FMA. It really is that simple. We're going to figure out what the forces are, equate that to a effective force diagram, make those two the same, and compute what that needs to do. So given some masses and the forces, find the acceleration, vice versa. We know acceleration and forces, we could find mass. We can flip this any way we want to. And that's honestly the heart of it. So it's not any more complicated than that. However, the implications of it generally get where we get into our complicated detail. So let's talk about the idea now of the first and third law, where we're going to have the idea of inertia. So inertia is the state at which a body wants to be acting. So if we have an inertial force, an inertial force is a force that acts, that is part of the body, and it is internal to the body itself. It is not actually acted on, a force that's acting on the body, but it's rather the body's, a particle's internal reaction to forces acting on it. So if we had a particle and we had a bunch of forces acting on it again, I'll just do 2 this time. Then there is some inertial force that those forces must overcome if they want the object to move, or there must be some they may change the action that's going to take, right? So by first law, we know that the inertia of an object only changes when it's acted on by a force. And now we can take the implications of the second and third law and figure out, well, what is that inertial force equivalent to? So the implication is that if there is an equal and opposite reaction, then that means this also must be the same thing as what we'll call the inertial force, and it will be in the opposite direction. So we've got some sum of these forces, F, and it will be equal to, but have an opposite direction as the mass times the acceleration. So that is taking the second law, that we know the magnitude of that inertial force has to be equivalent to mass times acceleration. And because we're talking about the internal reactions, then we know that internally that inertial force that must be overcome by some forces in order to get an object to move must be equivalent to its mass times acceleration, but simply pointing in the opposite direction of the resultant force vector. And that will be a vector. So let's go ahead and put a hat on it and make sure that our accelerations have hats too. So why would you care about the inertial force? And we don't typically put inertial forces on our free body diagrams explicitly because they are not external measurable forces that we are putting onto a particle or our body. So when would we use it? And that is a couple different cases, and I kind of hinted at it earlier, right? So when we want to get something started moving, or we're afraid that something will start moving, that's the case where we're going to be careful and want to know what are the internal inertial forces that some external forces must overcome, or we don't want them to overcome, in order to get an object to move or not move, depending on what our goal is. So if that's the situation, that is a special case where we call it equilibrium. And in an equilibrium state, it means that the sum of the forces that are acting on the body are going to be equal to the inertial forces, and then there will be no acceleration of the body out above beyond that. So that's basically saying the sum of those forces is going to be equal to the inertial, which is that mass times acceleration. So that's a particular situation when we'll look at what types of forces is it going to take to get an object to start moving, or how much can something be accelerating before it starts moving. That's when we're going to want to look at these situations of is our equilibrium no longer true, or what will it take for it to be true. So that's the special case where we apply the first law. So as we move forward with different aspects, we're going to look into detail of applying the force mass acceleration method to individual particles and systems of particles, as well as situations when we have objects that are acted on by certain types of forces, like a central force, and how that's going to affect the body's movement, as well as what coordinate systems we want to use to describe that motion. So that's going to be a focus for a while of applying the force mass acceleration method. And one implication of the force mass acceleration method is this idea of inertial forces and overcoming inertial equilibrium.